Hello guys, this is Ravi Rajput and welcome to my YouTube channel Next Gen Neuron. So today we are going to discuss another interesting topic in deep neural network, that is transformer. So basically transformers have gained a popularity in past few years, right? So they have evolved significantly in past few years and took over a wide area of artificial intelligence world, right? So they are pretty efficient to do various types of different tasks, I would say, right? So uh, they can do image classification, can be a substitute of CNN networks, what we have learned in past, right? So as a vision transformers, they can efficiently do the NLP tasks as well, right? So we'll learn more about transformers from NLP perspective in this video. So what is NLP, or natural language processing? So anything which deals with human languages, human language form, right? So human language type of responses or inputs, those are called NLP tasks, such as machine translation or sentiment analysis or question answering. So any type of task which is generating a human language type of responses or taking input as text or speech or whatever, so those are NLP tasks. So transformers are pretty good to do such type of things as well, right? So machine translation, for example, they can do question answering, like the BERT models are there, which can take which can perform machine translation and question answering, as well as GPT is another form of transformer which is widely used for sentence predictions, right? So it undergoes through a vast training on a wider data set and learns based on the masked prediction training and different other types of trainings, like so it learns about sentence predictions. So there is a lot of process behind the scene which happens. Based on that, transformers are doing their job. So let's understand more about transformers. Like, what is the magic behind the scene which happens so a machine is able to generate a uh, answer for you based on the question you had asked and from the passage which it has never seen, right? So let's see how it goes or how it happens. So in Transformers, the first thing you all should know about is a very fundamental concept of NLP, that is text embedding. So basically, text embedding is not only for Transformers, but wherever you're performing an NLP task, either in Transformers or any other model, you should know what's text embedding, right? So text embedding is in a single sentence. If I would say, text embedding is converting the text into numbers, right? So the machine does not understand the text directly. The text needs to be converted in numbers first, and then it needs to be processed. So I would create a separate video about text embedding in detail, right? So but for now, just understand that it's a conversion of text into numbers. So consider a token, consider a sequence or a sentence which needs to be processed in transformer for any NLP task, right? So for example, there is a sentence like lion is a king of jungle. Okay, so the lion is a king of jungle. So all so what text embedding will do, it will first tokenize all the word, I would say word as tokens, all the tokens out of the sentence. Okay, these will be tokenized in independent tokens, and all the tokens will be given its text embedding vector. Okay, I would say it as a feature vector. So it's a multi-dimensional vector assigned to each token. So for example, loin will have a feature vector as zero point 0.1, zero point 0.2, zero point 0.3. Is will may have 0.3, 0.5, 0.7. A may have zero point 0.4, 0.3, zero point 0.2. So those are the multi-dimensional vectors corresponding to each token, and so on, right? So uh, this is how the text embedding uh, does the tokenization of text, right? So it assigns a feature vector corresponding to each token. Now, what it will happen? So once the text embedding has been done and a certain feature vector has been assigned, then the interesting part comes, and that is specific to transformer. So that is known as the self-attention mechanism. So self-attention mechanism is a very crucial concept or a basic concept, attention mechanism, which will be used in transformer, and which is pretty useful to identify the contextual meaning of all the tokens, right? So the relevancy of all the tokens within the context. So I would explain how self-attention mechanism performs its job on the token and how it assigns the attention score to each token, right? So self attention mechanism, what it will do, it will process all the tokens came as an input, will assign the attention scores to each of the tokens. So loin will have a separate attention score, is will have a separate attention score, and so on. Jungle, king of jungle, all the tokens will have its their own attention score. And attention score is a kind of, is the weightage of that particular token in the sentence. So how much that particular token is relevant in the sentence, right? So for example, jungle, king and jungle may have, similar attention scores. Both are having a same weightage in the sentence, but is and a, these type of words may have a lower attention score. So transformer would know like which text they need to attend. They are not going to give the attention on is or a. They will give more attention to loin and jungle. That's a concept of self attention mechanism. Basically what it does, so self attention mechanism, it starts with calculating the k q v vector for each token. So for example, loin, okay, loin will have its own k vector, q vector, and v vector, right? Similarly, jungle, king, and every token is going to have their own, yeah, its own kqv vector. And further, the k vector of a loin. So for example, you are calculating the attention score of loin, right? So the q vector of loin will be multiplied to the k vector of all the other words. Okay, in case of calculating the attention score for loin, so the q vector of loin will be multiplied, or the dot products will be calculated, yeah, will be multiplied to all the other k vector of other letters, other tokens, okay, other words. So after that, once it is once the dot products has been calculated, based on the dot product, the softmax function is applied, and a normalized probabilities are calculated, or say probabilities are calculated, right? So that probability is then further multiplied by the v vector of all the tokens, and the weighted sum is the final output or final attention score. So this is just a basic, this some mathematical algorithm is performed behind the scene. I'll give the detailed video, separate video on self attention mechanism, but for now just consider like it to calculate the attention score, it multiplies the specific q vector with all the other k vector, yeah, calculates the dot product, and then calculates the probability and multiplies the weighted sum, and mm, gives the output, the final attention score. So again, just consider kqv. Basically those vectors are calculated based on the training of the model which it had gone through, right? So if your model has gone through the training of the forest data, then the line and forest may have a different attention score. But if it has gone through a different data set, so it may have a lesser attention score, right? So totally depends how the model was trained, what it has learned in its past. That's why we say, like, if we have trained the model on an astronomy data, or like space or planets related data, we cannot use that model to find out the answers for on medical data, or find out the contextual meaning in the medical data, right? Those KQV vectors totally depends on the training, right? So how the weights were assigned to it. So that's all about self attention mechanism. So as an output, each token in the sequence will have its own attention score. Okay, so for example, loin, king, jungle will have its own attention score, like zero point 0.8, 0.7, zero point 7, 0.6. So zero point 0.8 means the model will give the most attention to loin, right? And and so on, and relatively lower in king and jungle, and so on, right? So so once the attention scores have been assigned to the tokens, those are further processed to the next layer. So that is where the prediction happens or where the answer is found out. Like, so for example, in question answering task, you have asked a question, right? So question answering task, basically you are going to provide a context, like lion is the king of jungle, the jungle is pretty big, and the question, who is the king of jungle. So again, the question is also the question and context both are going to be processed as a single input, right? Embedding is going to happen, going to attend, yeah, going to generate the attention scores out of it, right? So it will identify, so who is the king of jungle. So once the contextual vectors have been generated as an output of this entire process, right? So that those contextual embeddings are ready to give you the answer, the most similar and most suitable answer out of it. So if there is a question which was processed again as a token embedding, it will have its own scores and everything. It will find out what's the king. Oh yeah, so who is the king of jungle? Then automatically the transformer layer will pull out based on the score. The answer will be lion. So that's the entire magic goes behind the scene, how uh, NLP models are able to identify the context or the words, right? So, or the answers, or they do the prediction. So, yeah, so that's about a very high level. What's the mechanism? So, uh, going forward, there is, let's talk about the architecture of transformer models. Okay, so one is encoder and is decoder. So basically transformer architectures consist two components in it, which is encoder and decoder. So whatever the process I had explained. So encoder and decoders, the first thing, encoders and decoders are used as per their necessities. If and different transformer architectures use different components, like for example BERT, which is mostly used for question answering and machine translation task, that uses encoder and decoder both, and GPT as chat GPT, right? So it's a generative pre-trained transformer, which is mostly used for sentence prediction, right? The next word prediction. So that does not need a deep understanding of the context. That's why it uses only decoder. Encoder is not needed. Remember, encoder is only needed where there's the requirement of a deep understanding of the context. In question answering task, if you are providing a big context, a long passage, right? Model needs to understand the entire context thoroughly so it can produce a suitable answer for the question which was the input, right? So in that case, where the understanding is the key, where the model needs to understand the context, it needs encoder. Otherwise, for the sentence prediction, it's just a very straightforward thing. Model has been trained and vast amount of data, going through the mass prediction and different type of training processes. It learns what should be the next word of the sequence, right? So the lion is the king of, it will predict jungle, right? So we don't need the encoder in those types of architecture. So these are the two different things, like BERT, which needs encoder decoder both, and GPT needs only decoder. So and they have their different purpose. So if needed, I will see if I can create a separate video for BERT and GPT, but that's pretty much right. So how those are differing. For sentence predictions, only decoders, and for deeper understanding, question answering, machine translation task, where the understanding is needed from both the direction. It needs to go from left to right, right to left, to understand the entire passage or entire context. We need encoders in it, right? Okay. Another topic is I would like to cover is fine tuning of transformers. Okay. So what's fine tuning? Okay, uh, there is a website on internet which you can search Hugging Face. Okay, Hugging Face is a website which is holding many pre-trained transformers. Right, it's having bunch of GPT and BERT models which were pre-trained on a vast amount of generic data set. Right, they know their job. Okay, so now you want to use that. So those are ready to use. You can simply download the model, put a question context, I will give you the answer, because those have been trained precisely on a generic data set. But if you want the model to provide the answers based on your data, right? If you have a business of education, for example, and you want the model will generate the answer specific to your business, then you have to fine tune it based on your data set. You have to perform another round of training on your data set. You have to prepare a big data set, will and your model will go through training, learning, updating it weights based on your data set, and will learn how to give the prediction or how to generate the answers or how to generate the outputs which is more specific to your business, not the generic one. So then the fine tuning comes. You have to fine tune the model. You have to do a separate and additional training which will override its previous learning, but it will take the new learning in consideration, which is suitable for your business. So I would create a separate detailed topic, the coding exercise, how the fine tuning is done. I would use PyTorch. I would show you how that how that training is done on a separate data set. I will use any pre-built data set and will show you what's that fine tuning is about. Basically, it's a kind of training of transformers, right? So for this theoretical mm, video, it's pretty much this is the basic understanding how in NLP task how transformer tokenize the words, and then based on the self attention mechanism assigns the attention scores, so by which it learns like which token it needs to give the attention based on the question. The attention scores may be changed, and accordingly it will generate the answers for you. So that's the magic goes behind the scene. So hope that's clear, but I would definitely keep on covering the transformers in other videos, like in practical examples or demonstrations. And for more information, please keep on reading the stuff on our website, which is styrisci.com, as well as blog.nextgenneuron.com. So you'll get more stuff there, and we'll get more grip on these things. Yeah. Thank you so much.